Welcome back. So we return from our side quest looking at special types of orbits, and in this segment we will summarize what we've covered so far on where satellites orbit and transition into our next major topic, how satellites get into orbit. So we started this module by defining where space begins, the Karman line at 100 kilometers above the Earth's surface. And we discussed what it means to be in orbit. An object in orbit is in free fall around the Earth. And a satellite is similar to like a ball being dropped, but in order not to hit the surface, the satellite needs a huge amount of horizontal speed. For an object in orbit around Leo, it needs to be moving at 7.5 kilometers a second or 17,000 miles per hour. And the speeds to orbit in MEO and GEO are similarly fantastic. What we haven't yet talked about is how satellites get into these orbital regions. I mean, like, sure, satellites are launched from Earth on a rocket into orbit, but how does this really happen? So to think about this, let me ask what seems like a random question. So what happens if I jump straight up? Well, if I jump up, I leave the ground with some speed, but gravity is always pulling downwards. At first I slow down, and then I pause for a second, and then I reverse directions and come back down to the ground. What sets how high I jump? Well, it's the speed that I leave the ground. And if I want to jump higher, I need to leave the ground with more speed. So maybe I could leave the ground with so much speed that I could jump up and actually make it to space, say to the Karman line. And this is possible for a small rocket. There's a decent number of YouTube videos out there from rocket enthusiasts, say like a bunch of university students, launching a small rocket equipped with like a GoPro into space. But all of these small rockets go up and then come back down, just like when I'm jumping. And even if we launch a super powerful rocket that can easily reach space, if it's launched straight vertically, the rocket will most likely be pulled back down by Earth's gravity.
Let's go science!
The only way not to fall back down if you're launching vertically is to leave the ground with what's called the escape velocity. The escape velocity from Earth's surface is really, really fast. So 11.2 kilometers a second or 25,000 miles per hour. And note that's faster, 1.5 times faster, than the horizontal speed we need to achieve a LEO orbit. That is, it's easier to get into orbit by launching with some horizontal velocity than it is to launch purely vertically and not fall back down to Earth. But if I'm stubborn and really want to launch vertically, one of two things can happen. So one, I can launch straight up and be pulled back down. Or two, I can launch with a vertical velocity greater than the escape velocity, 25,000 miles an hour, and leave Earth's gravity for good. But note, if I launch vertically, I can never go into orbit, no matter how fast I'm moving. If I don't care about going into orbit, say I'm heading to Mars or beyond, the second option, launching with the escape velocity, is something to consider. The first option, launching but getting pulled back to Earth, is called suborbital flight. A suborbital flight is something that gets above the Karman line but doesn't make a complete orbit. And it's the same if an object goes straight up and then is pulled back down, or if it has some horizontal velocity but not enough to make a full orbit. And in principle, when I jump up, this is kind of like a suborbital flight, but that word is reserved for something that can actually jump above the Karman line, and that's not me. There's some very famous suborbital flights. So in 1961, Alan Shepard became the second human and first American in space. Shepard made history on a suborbital flight that lasted 15 minutes and reached a height of 180 kilometers above the surface. Fast forward 6 decades, and you can now buy a ticket for a suborbital spaceflight. One of the rockets taking tourists on these suborbital spaceflights is Blue Origin's New Shepard rocket. All you need is a hilarious amount of money and like some Dramamine. We started talking about suborbital flights in the context of launching vertically. If I want to make a complete orbit, we cannot launch straight vertically. Most of the effort must go into moving in the horizontal direction. And again, to achieve orbit, we need a horizontal speed of 17,000 miles per hour. Coming back to an image we showed a while back at the beginning of this module, we had a cannon firing satellites into orbit entirely horizontally. The reality isn't actually all that different for real launches. As soon as a rocket clears the launch tower, most vehicles will begin to pitch over slightly and head in the direction of its orbit. Launching vertically at the very beginning is good for not hitting the launch tower or mountains or whatever, but there's actually an additional advantage to beginning the ascent vertically. Moving vertically at first means a rocket passes quickly through the thickest part of the atmosphere where there's the most air resistance. And as a rocket gets higher, there's less and less atmosphere, which makes it easier to accelerate. But the faster a rocket is moving through the air, the harder it is to move. The analogy here is like trying to run through a swimming pool, right? It's harder to run faster in a swimming pool than it is to move slowly. There's a point where these two effects cross. The rocket is getting faster, which makes it more challenging to move, but the atmosphere is getting thinner, which makes it easier. And the point at which these two competing effects meet has a name. It's called max Q. Max Q typically happens about 1 minute after launch, 10 kilometers or so above the ground. Max Q is also the moment at which the physical stresses on the rocket are the greatest. This means it's also stressful for all the humans involved as well. If you're listening to a launch, you can often hear the announcer's voice state that the rocket has passed through max Q and then relaxed noticeably. A rocket headed into orbit will begin deviating from pure vertical once it clears the launch tower, but after max Q, most of that effort will go into achieving the horizontal orbital velocity. Whether launching into orbit or even faster to reach the escape velocity, the speeds needed to reach space and stay there are incredibly large. A nice way to summarize this idea is that getting into space is easy. The hard part is actually staying there. So to avoid falling back down to Earth, you have two options. First option is to go sideways really, really fast, that is to go into orbit, or do something even more difficult, which is launch faster than the escape velocity. Either way, we're going to need a really, really big rocket. So in the next module, we will focus entirely on rockets. How do they work? How are they different from airplanes? And why it's so darn hard to get the velocities we needed to stay in space. So see you over there.